Peroxyacidic acid has a different formation. In our cyanidate formation, is these two work together. So this somehow 23.5%. This PAA is about like maybe 5%-ish, and the others are water. Now, if we take this thing out, why this guy is a very good antimicrobials, and I tell you the reduction level is higher than these weak acids. This is 1 to 2 log. The PAA somehow could reach maybe 2 to 3 log. Well, certainly depends on different products. But why? If we talk about the lipids oxidation, we will know that very clear. The reason is this guy could release. And you can imagine this is a very short chain fatty acids, and this couldn't release become this guy. What is this? Hydroxy radical. Remember, when we talk about lipids oxidation, we said if the hydroxy radical, if it's released, it basically can oxidize any fatty acids, including saturated fatty acids. Now we go back to see the fluid mosaic model. So what happened? I'm going to draw here. Oh, okay, very, very simple. Everybody knows this fluid mosaic model. We talk all the time in different classes. Okay, it's bacterial cell. That's what? Peptidoglycan. Okay, so you have a double layer here. That's everybody knows. For gram-negative bacteria like Salmonella, like E. coli, and on the top, that's LPS. Okay, now we talk this out. And I know, you will remember that's hydrophilic, that's hydrophobic. Yeah, lots of people just remember, and then they will mess up sometimes during the exam, especially the freshman students. But I tell you a way you will never forget if you know the structure. So what it looks like. That's a head. And then go here. That's a phosphate. Then you go here. Then you go here. This is C16. This whole thing is this guy. Why? The hydrophobic head. That's ethanolamide. What it means ethanolamide? It's like you can understand it like an ethanol-like material. And this thing's going to dissolve into water. It's hydrophilic. It's a phosphate. What is this one here? A standard is palmitic acid. And I said This can basically oxidize anything. Okay, what we do? Attacking here. How much energy we need? It's just more energy. Kj or more. That's the reason. Because it's oxidized impacts. The mechanism here is much better than this guy. Because this is permanent, could be, which is oxidized. And this is bacteria has a way to combat with exchange of like potassium or those things. And this has been done a lot. This is recent 10 years it come out, and that could be approved as an organic process. Now, what is the LPS? I'm not going to draw the whole thing, okay? LPS on the top looks like this. Somehow like this. That's on the top. Only a model. That area, lipids A. So you go down here, they have all this core area. And you go here. That's also a fatty acids chain. Sorry, that's lipids. I go the other way. This is polysaccharide. This is sugar. Polysaccharide. We'll talk real quick next week. This is lipids A. That means this will be attacking point by here. So, if you look at this figure, we haven't get to these yet. I believe that the research has been done. If you have a hydroxy radical, a very energized, we call it electrophilic products comes out, they could oxidize the phosphorylator of the cell membrane system of a gram-negative bacteria. Remember, gram-negative bacteria have two layers. And then lipopolysaccharides on the top. And the lipopolysaccharides contribute to what? That's the endotoxin. That's why this damage is much more permanent compared to here. Here is, said very honestly, is just let the bacteria become tired. But they could always recover. This is like you're running half marathon, you can always recover. This is like take out their bones. So that's why you see the reduction, the reports for the reduction of PAA somehow could be 3 log, 2.5 or 3 log. But this way, you can only see it's about 1 log, sometimes 0.5 even. The research published in the Poultry Science, you see those raw chicken carcasses, it's about like less than 1 log reduction. And the 1 log reduction is the best because there's a restriction for that. So, if you don't know about these mechanisms, a simple mechanism behind that, you are feeling it's very boring. When you ever see the publication, they always like 1 log. Maybe there's 100 paper, or 300 paper, 500 paper, talk about all these weak acids. They're about 1 log reduction, 1.5. That's the reason. And when you go to PAA, encoding like chlorine, chlorine dioxide, other oxidized reagent, they could be have a much higher reduction impacts. The reason is these mechanisms are different. The way why we want to explain here, because we talk about lipids oxidation is just long. Here, but we don't really recognize. If we took out all these CH2, all those alkyl components, it could be as short as right here. It's a PAA. And we didn't recognize that. And we didn't recognize these antimicrobials is a very short chain fatty acids. So that's a combination between for the chemistry and the microbiology. But we didn't recognize that until we learn from here. That's interdisciplinary knowledge could be combined together. That's why this is usually I end up with the section of the fatty acids. And we could well connect it to our lab, the activities have been done. I have been done like 20 years of those antimicrobials, and it could be end up very well with you. Okay, so that's what we have.